Yeah, so I'll be talking about the Hadean today, and we know that there's life on Earth, obviously, and I would venture a guess that most people believe that life originated quite early, so quite possibly during the Hadean. So I'll be talking about what we have learned from the mineral zircon about what Earth was like during the Hadean at a time when life potentially originated. So here we are looking at a Hadean zircon. So this one is from South Africa, and you see this beautiful oscillatory zoning really telling us that we are looking at some type of like primary zircon signature that we can use to interpret the deep past. So for the agenda today, so we were asked to give a brief introduction of who we are. So I'm going to do that first, and then I'll talk about what do we actually have preserved from the Hadean eon, which is not a whole lot, but it's something, and we're desperate, and we're trying to learn anything we can about that time period. Then I switch to talk about the habitability of the Hadean Earth, and it's really a question of, what is required for a habitable Earth, and what can we learn from zircon about those requirements. So those include, having a crust instead of a magma ocean, and the tectonic regime we are in is the evidence for liquid water and weathering. What do we know about the atmosphere from these zircons? What can we learn about that? The presence or absence of a geodynamo, and then, of course, lastly, life. So just really briefly about me. Again, I'm Nadja Drabon. I'm an assistant professor at Harvard University. I've been there since 2020. That's when I started a postdoc there, and then 2021 I officially started my position. Beforehand, I was at Stanford University, where I got my PhD, and my undergraduate I did at the Free University of Berlin, so you can probably hear my German accent. So in my research, I'm really interested in the early Earth. So when we think about the origin of the Earth, right, we initially think about this planet that was generally uninhabitable, right? Earth was initially covered by a magma ocean. We had frequent meteorite impacts. And that's in part why we call it the Hadean Earth. So Hadean comes from Hades, the Greek god of the underworld. But then through 4.6 billion years of history, right, we transformed from this type of uninhabitable planet to forming the first crust, having the oceans condense, the initiation of plate tectonics, onset of continent formation, to a planet that we are looking at here today, which has this bimodal distribution in surface elevation. So we have got the differences between continental crust and oceanic crust. We have plenty of water, and of course, there's abundant life on Earth today. So the question really is, how do we get from this uninhabitable Earth to Earth as we see it today? To do this type of research, I use the sedimentary rock record. So I'm trained as a sedimentologist, and sediments really provide this wealth of information about all sorts of different aspects of Earth's surface evolution. So when we think about the generation of sedimentary rocks, we first, of course, think about a source. So let's say we have got some form of uplift, we form our mountain belt that's being weathered and eroded to form sedimentary rocks. And those sediments are forming here, then they're being transported downstream and ultimately deposited in our basin here. So throughout this time period, the sediments are recording all sorts of information. So that includes information about the crustal setting and the crust evolution, right? Because our sediment grains, if you have quartz, feldspar, all types of different grains, lithic grains, they're going to reflect the source. So you can learn about the crustal evolution in the hinterland. But not only that, with the changing composition of our sediment, this can tell us about the nature of tectonic uplift. And of course, when we look at the sedimentary response, right, we are looking at basin formation. So different tectonic basins or tectonic settings have different types of basins. We can look at the basin evolution, which again can tell us a lot about early tectonics. But of course, during the process of being generated and transported to the ultimate depositioner site, sediments record a whole bunch of information about the interaction with the atmosphere. So during weathering, interaction with the hydrosphere, right? How is the sediment being transported? How is it being reworked? And then, of course, early life. So most of our evidence for life throughout Earth history is recorded within sedimentary rocks. And then, last but not least, we can learn about the effects of giant meteorite impacts during the early Earth. So the early Earth is really controversial, but that there were a lot of meteorite impacts is something that's generally accepted. So sediments record kind of what happened, what was Earth like before some of these giant impacts, and how did it change after. So today I'll be focusing mostly first this morning on the crustal setting, crustal evolution, and generally what we can learn kind of about the provenance of these zircons, right? Where they're coming from, what does it tell us about the magmas they're forming in, and all of that. And then later this afternoon, I'll talk about the effect of giant meteorite impacts on the early evolution of life. All right, so just a quick recap. We are looking at early Earth history, and the two eons that we are really interested in for today is the Hadean and the Archean. So the Archean goes from 2.5 billion years ago to 4.03 billion years ago. So the boundary between the Archean and the Hadean was recently changed to 4.03, and it's marked essentially by the oldest rock on Earth, which is the Akastak gneiss. One problem that we face is that there's extremely little material left for the Archean. So when we look at the world map here, so all these dark gray areas that you are looking at, so these are all Archean cratons. So you can see there's a few of them, but actually, although it makes up this really substantial chunk of Earth history, only about 5% of rocks exposed at the Earth's surface today are Archean in age. And not only that, a lot of those rocks have been through a lot, right? They have been cooked, they have been deformed. So in a lot of cases, the rocks have been altered so much that it makes it really hard to interpret kind of the original composition and what they tell us about Earth's surface environment. And then, of course, as we get to the Hadean, just by definition, there's no Hadean rocks on Earth. But then luckily in the 80s, people identified Hadean zircons. So this is in Western Australia. So you can see that over here. By ion microprobe, they identified zircons that were between 4.1 and 4.2 billion years old. And that was a huge advancement. So beforehand, no old zircons had been found, and that kind of settled this idea in people's head that the early Earth was absolutely uninhabitable, potentially just covered by a magma ocean, so that you wouldn't form like any crust or anything. So it really painted this very hellish picture of the early Earth. But since this discovery, our idea of the Hadean eon has really substantially changed. So there was the first paper, and then 1986, they found more Hadean zircons, this time in the Jack Hills. I really like the title, Jack Hills, evidence for more very old detrital zircons. And the Jack Hills is really this famous area that probably everyone in this room has heard about. So this is where most of the research has been done on the Hadean eon. So you're looking at this meta conglomerate here. And I don't know, there's been tens, like maybe even 100 papers published on these zircons. So why is zircon so great, right? Why do we focus on zircon? Why don't I talk about like biotite or apatite or anything else? Well, zircons are really a fantastic archive of the early felsic crustal evolution. So in this statement here by Roberts and Spencer, they say zircon is arguably the best archive of Earth's. They initially said continental crust, but what's important to note here is that zircons don't only form in continental crust. So even in more primitive or oceanic settings, you're able to form zircons, and differentiating between those, more primitive origins or juvenile origins versus continental origins is something that's going to become important later in this talk. So why is zircon so great, and why it should be everyone's favorite mineral? Well, again, it's really common in siliceous crust, and then it's really durable. So I was talking earlier about, you form these mountains, you're weathering them, you're transporting it downstream, right, sometimes for thousands of kilometers. But zircon is just a really hardy sediment, and it can survive all of this transport. And then, maybe even most important of all is that we can date it. So when zircon forms, it incorporates uranium, which is going to decay to lead, and we can use that to actually date the age of the zircons, which in a lot of other minerals is a little more tricky to do. And then lastly, what is exciting about zircon is that it retains a lot of information. So zircon itself is composed of, zirconium, silicon, and oxygen over here, so we can probe those different elements, but there's actually a whole slew of other elements that are incorporated into the zircon. So if we measure the isotope geochemistry or the trace and rare earth element geochemistry, it's going to be kind of a mirror of the magma from which the zircon formed. And we know quite a bit about magma genesis, so if we can probe the chemical composition, we can give a little bit of information about what type of geodynamic settings the zircons formed and what kind of material was incorporated into the melts. So it's actually a really powerful proxy. All right, so just let me give you a little bit of more background about how we date these zircons, so how we came up with these really old ages. So when we have a magma, right, we have a lot of lead and uranium sort of floating around. And when the zircon forms, what's special about it is that zircon incorporates only uranium and essentially no lead. So when the zircon crystal first forms, you can see here lots of uranium and no lead. But then with time, the zircon starts, or the uranium starts decaying. right? So you're producing more and more lead that's going to accumulate within your zircons. So to ultimately here, so pretty old zircons, you mostly have lead and no uranium. So what we do now is we look at the uranium versus lead concentration, and that can give us an age. And the kind of how we do it is one thing that's like additionally exciting about zircon is that we don't only have one decay series, but we actually have two. So when we date zircons, we have these two decay series, so we can like really double check our ages to feel really confident about them. So for both of those decay series, they are really well constrained, right? We know the decay constants really well. They're really hard to reset, allowing us to really firmly date the zircons. So this zircon here, I put this one in before they redefined the onset of the Hadean. So up to a few months ago, the zircon was Hadean in age, but now because it's younger than 4.03, it's actually not even Hadean anymore. So sorry, little guy. All right, so where have we found Hadean zircons? Again, everyone has heard about the Jack Hills, and it's really famous, and people have gone in with mining equipment, and then they have identified more than 10,000 Hadean grains at this point, which was a huge effort, and people spent careers doing that, and they've really advanced our understanding of the Hadean Earth. However, as you can see, there's a dozen other locations around the globe with Hadean zircons. So most of them have like only 1, 2, or maybe 3 Hadean grains. So these Hadean grains, as you can see in this image here, are tiny, right? They're the size of a grain of sand. But again, there's like about a dozen other locations around the globe that we could be probing. And then there was a relatively recent new discovery, and that's one that I've been working on quite a bit, and that's the green sandstone bed in South Africa. So there, to date, we have found 92 Hadean zircons, which, pales in comparison to the Jack Hills. But when we think about, if we want to probe the Hadean Earth, an n equal 2 is better than an n equals 1. And it's something that we're constantly building on. We're also looking at zircons, Hadean zircons from India now. So hopefully we are going to start fleshing out like a better picture of the Hadean Earth. You can imagine, right, if you are dropping down on Earth today in a random spot and you collect a sample of the crust, it's not going to be representative. Right? It's only one location. So really what we need to do, and what I hope we'll be doing in my lab over the next couple of years to decades, is like probe a few other of these locations to really better constrain what the Hadean Earth was like. So these are the 3 locations where the most Hadean zircons have been found to date. So let me just compare those a little bit. So we have got the Jack Hills over here. So the sediments themselves are 3.3 billion years old. And as I was saying earlier, right, you've got the sedimentary rocks, and they're going to be composed kind of a mix of what was in the hinterland, right? The rocks that they're being weathering and then transported into conglomerate or sandstone. So the Jack Hills are 3.3 billion years old, and they've been quite intensely metamorphosed, so up to amphibolite facies metamorphism. So they've been cooked quite substantially. On the positive side, they contain quite a few zircons. So when you date the zircons, between 3 and 12% of the zircons are Hadean in age. Now, the green sandstone bed has a few advantages and a few disadvantages. So the green sandstone bed itself is a little bit older. It's 3.3 billion years old. And this one has only been cooked to green-schist grade metamorphism, so much lower temperatures, and really is excellently preserved. So you can see these fine laminations here at the millimeter scale. Here you see some rip-up class of carbonaceous chert, so really excellently preserved. However, only 0.5% of the zircons are Hadean in age. So we need to really date thousands and thousands of zircons in order to find like a significant number of Hadean grains. And then lastly, we have got the older metamorphic tonallitic gneiss in India, which is about 3.4 billion years old. And this one is a little bit different because it's not a sediment, but it's an actual igneous rock. So what happens sometimes when you've got these magmas rising towards the surface is they kind of like contain a lot of other material and like older material that kind of gets, sucked up by the magma. And sometimes you get some of those older zircons preserved. So they don't necessarily melt and then you form new zircons, but you've got these old zircons preserved and then you form also new zircons. So those are called xenocrysts. So kind of like crystals that were like acquired previously. So looking at the ages of the minerals, so here I'm just comparing the Jack Hills over here in South Africa. Again, they're detrital zircons, so they're sedimentary zircons. So they're going to contain this huge range of ages, right? Because we've got all these different other kind of igneous rocks in the source that are being eroded into. So for the Jack Hills, you can see there's a major peak about 3.38 billion years, then the ages tail off, and then you have a small peak here about 4.02, 4.18 over here. So in South Africa, in the green sandstone bed, we get a similar really young age peak, and then again a few older zircons, and this teeny tiny peak over here that's about 4.1 billion years old. Just a quick note, so this is an order plot, so now we are at about 30,000 zircons that we have dated in total. Again, because of that, now we have got about 100 Hadean zircons. All right, so let's think a little bit more about what do we want to learn from these zircons, right? We're really probing them, taking them apart in every way we can think of. So what is really interesting when we think about the question of the habitability of the early Earth? So as you all know, a habitable planet is one that can sustain life for a significant period. And there's a bunch of different geological factors that make Earth habitable. And every person in this room will probably give me a different number of factors that make Earth habitable. So these factors here are from a book that Mark Harrison wrote, who's done a whole bunch of research on the Jack Hill zircons. So of course we want to be in the habitable zone, allowing us to have liquid water. We want to have the right composition, right? We ideally want to have kind of like a solid or at least a liquid kind of surface, and we want to have abundant carbon, nitrogen, oxygen, all of those things. Considering, sorry, the pointer is just really off. We have to think about the planetary mass, right? Because if we're too small, then we can't retain the atmosphere, and the planet is going to cool down really fast, and the planet is basically going to become inactive that way. Impacts are important because they're sort of a double-edged sword, but they might have contributed a lot of the important elements for life and potential building blocks for prebiotic chemistry. Satellites are important. They allow for the tides, and they're going to stabilize sort of the climate of the Earth, and they're also going to allow a lot of ocean circulation, which is important, especially in shallow water environments. And then we want some amount of heating, because the heating is what's going to drive kind of the surface cycling and all of that. So all of those aspects, we are pretty sure that we had them during the Hadean, right? I mean, we have them now, so I don't expect that Earth changed, 4.3 billion years ago from being like a gas to like being solid. But it's really like these three things on the other side that we are curious about and that we can actually probe using the zircons. That's firstly the question of, was there water? Right? Water is one of really the essential ingredients for life. Can we find evidence for it? Then surface cycling, which is basically the Earth's way of cycling important ingredients, nutrients, carbon, all of that between kind of the surface Earth and the interior Earth. And then the geodynamo, which provides a protective shield for life. So a different way you can think about this, and this is kind of more phrased in the way that we geologists think about it, is that on Earth, we have got these three different spheres, right? We've got the lithosphere, the hydrosphere, and the atmosphere. And all of those are going to be interacting with each other to create an environment that's really important for life. So really what we are curious about is how these different spheres are interacting. And we can look at it this way. So this diagram is essentially going to be the outline for the talk today. And it shows some of the aspects that we can probe with the zircons. So the first thing is, was there liquid water, right? Darwin's one little pond, so ideally you want to have some evidence for liquid water. Then there's the question of, crust formation. So we need a solid crust for life to evolve, right? The magma ocean is not going to help us. But not only that, when we can think about geodynamics and tectonic processes. So considering, for example, plate tectonics, it's one of the most efficient ways to create continental crust. And continental crust might be able to actually emerge above sea level. And when it emerges above sea level, it's going to start interacting with the atmosphere. So the atmosphere is going to be determined to a large extent, not entirely, but a large extent by outgassing. And then this atmosphere is going to interact with the emergent crust through weathering and erosion. And that's really important because it's going to stabilize our climate through silicate weathering. But of course, also it's going to release nutrients into the ocean. So we can look at this diagram here from Howe et al. We're looking at the phosphorus flux, basically a comparison against the modern. And when you look through time here, it's really a question of how much topography there was. A lot of the phosphorus that's being put into the oceans today is coming through riverine influx from continents. So you can see if you rapidly start developing topography, you're putting a lot more phosphorus into the oceans versus if topography only started happening, or like crust only started emerging later. And then another aspect that's important is just the question of having emergent land, and which will create different environments. So everyone can agree, or I think one setting that's been really proposed for the origin of life is hydrothermal settings. And especially in recent years, there's been a big push towards, that life might have originated on land, so potentially in terrestrial hot springs. For that, so you need some emergent land. And again, if you form continents, it's a very efficient way of getting this emergent land. The other possible site for origin of life, of course, is deep sea vents. And those also are going to be, if you are, for example, in a plate tectonic setting, you're going to have more deep sea vents when you are like in mid-oceanic rich environments and things like that. Yeah. All right. So now we're going to look at our zircons, right? So what can we learn from these zircons? But before we can do anything, we need to get the zircons out, right? So we've got our sandstone sample. It's going to be 99.999% not zircon. So we got to get rid of all of that stuff. So we use all these different separation techniques, like a water table, which is essentially what people do for gold panning. And we use heavy liquid separation, magnetic separation. And then if we're lucky, we end up with just like a pile of zircons. So you can vaguely see it over here. You see all these tiny little specks there. So all of those are zircons. Again, they're the size of a grain of sand. We put them on an epoxy mount. And then we just like shoot at them with whatever we have, right? So here this poor zircon has really been taken apart. So you can see we usually start off with our age analysis, because at first we just need to figure out which ones of our grains are Hadean in age. And then we look at hafnium isotopes, trace elements, oxygen isotopes, all sorts of things to learn about the early Earth. And it's really something where anything that's new that's being developed in terms of like how we can like understand zircons, what the chemistry tells us, we try to apply it to the Hadean. Again, we're just trying to learn as much as we can because it's just such an important time period in our Earth history. For that, so we take these zircons apart. We need to be really careful because the zircons are old. They're going to have cracks. They're going to have kind of these altered zones along the rims. So we really want to try to avoid those. And then we put them in all these different types of fancy instruments, again, to shoot at them and learn about them. And just a small side note, so I'm like drawing the Hadean zircon here as pinkish in color, and that is because they are pink. So zircons, these ancient zircons, because they've accumulated so much radiation damage from the decay of uranium to lead, they actually change in color, and they have these beautiful little pink grains. All right, so let's dive in, right? What have we learned about the Hadean eon? So first I'm going to focus on the crust formation and early tectonic processes. So, and there are some really key questions that we can ask about the evolution of the early crust, and that is, based on the zircons, what's our earliest evidence for crust, right? What type of geodynamic regime did the early crust form in, and like what types of crust were present? And these questions, right, the answers are becoming, because of our limited data, the answers are becoming more and more speculative. But let me walk you guys through them. So first the question is like, what type of crust was there? And the generation of continental crust has been like a really huge problem in Earth history, really understanding when did continents start forming. And here you can see this graph that many of you have probably seen before, right? So this is the cumulative volume content of continental crust. So 100% would be the amount of continental crust that we have today. And here we are just looking through time. And so you can see here that basically any type of scenario has been proposed, right? Some people suggest that continents started forming basically from the onset of Earth's formation and then remained essentially constant throughout Earth history. Then you have kind of the opposite idea that continents only really started forming about 3 billion years ago and then either started rising slowly or rapidly. And then you've got anything in between. So it's really still wide open. Again, one of the big controversies or the big issues in Precambrian geology. And the question of continent formation really closely mirrors that of the onset of plate tectonics. Because as I was saying earlier, plate tectonics is just a very efficient way of forming continents. It's not the only way, but it's a very efficient way. So here we are looking at a different type of diagram. So here time is kind of like going along this, like a clock. And each of these black arrows here represents a time period of when people have proposed that plate tectonics started. So it's basically any time in Earth history you pick, right? Like as early as like 4.2 billion years ago to as late as 850 million years ago. Again, plate tectonics is just so fundamental to like the surface environment of the Earth. Right, it affects every aspect of it, right? The fact that we have continental and oceanic crust is like entirely determined by plate tectonics. And plate tectonics just has this huge implication for habitability and the chemical circulation of the Earth, right? It's a really important control on the steady state composition of seawater, right? Because we are like subducting crust, but we are also outgassing waters, right? It produces the oceanic and continental crust. It transfers the elements necessary for life to Earth's surface, right? Otherwise, if we are just depositing material all the time, all of the important stuff would be just like gone and we kind of suck it out. But this way we really have the cycling here where stuff gets deposited, it kind of gets subducted, and then it kind of gets put out again through, you know, uplift or through outgassing. And then also plate tectonics itself is important for the mantle because it adds water to the mantle, which lowers the viscosity and is important control on active convection. All right, so what are people thinking about what the Hadean was looking like in terms of geodynamics? So the starting point, of course, is that we started off with the magma ocean, right? At least after the moon forming impact, or there might have been multiple magma oceans, like the last one being, you know, maybe the moon forming, after the moon forming impact, maybe there's another one later. And one option is what I call the uniformitarian hypothesis. So that Earth was pretty similar to today, and that there were active plate tectonics since at least 4.3 billion years ago. So that doesn't mean that the plate tectonics looked exactly the same like today. During the early Earth, we had this higher heat flux from the mantle, so the rheology of the crust would have been slightly different. So it wouldn't necessarily look exactly the same, but overall pretty similar. We still have mid-oceanic ridge spreading, and we have subduction really kind of driving the process here. And then the other hypothesis is the non-uniformitarian hypothesis, right? So we start off with the magma ocean, we form our early crust, but we don't have plate tectonics. So we have what's called a stagnant lid that was just covering the Earth. There was like a little bit of magmatism going on, right? There might have been like drips where kind of like crust is dripping into the mantle, or heat pipes where kind of the mantle is kind of venting to the surface. So this is the stagnant lid model where Earth would have started off with this. We don't have any active surface cycling, and then at some point later transition into the more active kind of lid environment. So this one way to approach this is by looking at hafnium isotopes. So we already heard a little bit about hafnium isotopes. I'm going to use them slightly differently here. So what we think about with hafnium isotopes is that 176 lutetium is going to decay by beta emission to 176 hafnium. And in general, hafnium is more incompatible than lutetium. So that means that the lutetium is going to preferentially try to stay in the mantle. Hafnium is going to go into the crust. And zircon is really great because it contains so much hafnium, so up to weight percent level, that it essentially freezes the hafnium isotope signature. So what we actually plot when we look at hafnium isotopes is the 176 hafnium, so the daughter product over 177 hafnium, which is a stable hafnium isotope. And when we look at the evolution of, CHUR, which is basically a proxy for bulk silicate Earth, through time, right? If we kind of Earth first forms, and then it's going to follow this trajectory here, right? Because we are creating more and more 176 hafnium through the decay of lutetium through time. Now, if we start forming continental crust and a depleted mantle, they're going to show a different evolution. So the continental crust is the depleted mantle. So if we are extracting continental crust from the depleted mantle, the hafnium is going to preferentially go into the crust, and the depleted mantle is going to retain a lot of the lutetium. So meaning that the depleted mantle is going to have more lutetium than the continental crust. So you're going to see kind of a steeper array here, versus the continental crust still contains a little bit of lutetium, but it's going to evolve at a much lower slope here. Now, zircon itself, again, incorporates almost only hafnium and no lutetium. A little bit of lutetium, but not too much. So meaning that the zircon is going to remain relatively stable. So the way we actually end up plotting this and how I'm going to show the data is that we kind of set the CHUR, so the bulk silicate Earth reservoir, to 0, just by definition. So if you have a depleted mantle forming, it should have a positive array, and then the continental crust or old crust should kind of follow this negative, should show increasingly negative values with time. So now if we're looking at zircon data and we are extracting crust from the mantle and you're crystallizing zircon from that, it's going to kind of have a mantle signature. So it's going to sit pretty high in our diagram here. So now if time passes, right, you formed your early crust and then time passes, doop, 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 and then you remelt it, then the zircons are going to have a more negative isotopic signature here. And then later on, if there's kind of you remelt the old, this crust here, and then you mix it with a new crust, so derived from the depleted mantle, then you should see this type of spread. So that's how hafnium isotopes work. So let me show you what the data actually shows. So this is data from all of the terrains where we found ancient zircons. So Hadean and Paleoarchean zircons here. And the first thing that you probably notice is that, you know, when we look at the ancient zircons here, so let's say anything older than 3.8, most of these plot either at shore at this red line or somewhat below here. So meaning that, you know, we don't really see evidence for extraction for a depleted mantle, but rather we kind of see early evidence for extraction here from, you know, like a shore-like reservoir and then continuous intracrustal reworking. Right, so in many of these settings, let's look at the Shingbum crater here in India, right? You see extraction from the mantle, and then we've got this crust that remains relatively isolated because we are not adding this juvenile material here derived from the mantle. And this is a signature that we see for all of the terrains that are this old. And it's really curious because, you know, when we talk about the early Earth and the Hadean, we really have to be really mindful of bias. Right? If we're only looking at one location and we see a certain type of crust evolution, it's not necessarily reflective of the entire Earth. But what is curious again about the hafnium isotopes here is that, you know, every location we look at for the early Earth, for the Hadean, shows the same signature. So early extraction from the mantle, and then the crust just remains isolated for hundreds of millions of years. If we had perfect data, you know, we could fit this array here, and like kind of how steep that array is going to tell you if it's more mafic or more felsic crust. But unfortunately, because, you know, there's quite a bit of scatter over here, we can't quite do it. So the other thing that's curious about this data set here is that at some point in all terrains, right, we go from this long-lived protocrust, and then suddenly we see this really high epsilon hafnium values. So this tells us, oh, now we've got new crust additions. So we go from a time period where we've got long-lived old crust that's just internally remelted to all of a sudden that is destabilized and you add new crustal material. And so we can see this over here when we put all of this on top of each other. I think it really shows it very nicely, though we have to be mindful that this data, of course, is going to be overwhelmed by the Jack Hill zircon. But again, we see this early crustal extraction, so as early as like 4.4, 4.5 billion years ago. Intracrustal reworking, and then starting at 3.8, we again, like everywhere on the globe, we start seeing very different signature. So this suggests that maybe there was an important geodynamic transition at that time period, about 3.8 billion years ago. What could that transition be? And people have interpreted the early record differently. So there's kind of, again, like going back to the two ideas between like early plate tectonics versus a global stagnant lid. So this plot here is from a paper written by Mark Harrison, who's done a lot of work, really pioneering work on the Jack Hills. And he's looking at the hafnium isotopes here. So the blue data is some of the original data that they first published that turned out to be contamination because they're mixing different domains in the zircons. As I was saying earlier, it's really important to place your splits really directly. But when you look at the red data here, so again, you can see it kind of plots below bulk silicate earth or chur and kind of along this crust evolution line. And they interpret this data to say that it's evidence for significant silicate fractionation early in Earth history, which makes sense, right? We are kind of departing from the bulk silicate Earth line and we're starting to form crust really early on, right? As early as like 4.5 billion years ago. And they interpret this data to reflect the production of at least some rocks of continental affinity. So they're saying early continental crust generation potentially relating to the onset to early plate tectonics. However, we've got the other interpretation here, and you know this was really a seminal paper by Anthony Kemp et al. In 2010, And they're looking at the same data set, and that's something curious you learn. People look at the same data sets of Hadean zircons and just interpret it completely differently. But they're looking at the same data set, but then they really go in and only pick the most pristine analyses that they can find. So they look at the images, they look at cracks or anything else that might have really altered your signature. Ideally, zircons where you have multiple spots on them, so you can be really sure that, okay, in 2 or 3 different spots of the zircon, we get the same signature. What does the most pristine data look like? And what they are saying is that, well, we lose all of the scatter if we do that. And it kind of the zircons start plotting on this line here, which is the slope of this line is very reminiscent of kind of like more juvenile or more mafic crust. So they say this doesn't reflect continental crust, but something more juvenile. And on top of that, they're comparing it to lunar zircons. So here the dots in white, and they're saying, well, we've got like the same signature, right? And the moon doesn't have plate tectonics, right? Mars doesn't have plate tectonics. So Mars actually also plots very similar to what we are looking at here. So they're suggesting, okay, there's actually no evidence for plate tectonics. This must reflect that we had a stagnant lead. We have this long-lived crust that is not being destroyed, right? In plate tectonics, we're constantly destroying crust. We're creating new crust. We just don't see any evidence for that. So maybe this reflects this global stagnant lead. So this debate has been ongoing for a really long time, and one possible approach to understand the origin of that early crust a little bit better is to look at zircon geochemistry. So for the people that don't think about igneous geochemistry every day, what we are looking at here is basically kind of signatures of melts that form in plate tectonic settings that are pretty characteristic of having plate tectonics. So what's important here is, right, if you have, like, let's say your basalt and you partially melt it, how does the geochemistry change that you're going to kind of find in your zircons then eventually? So if you have partial melting here without the presence of water, you kind of just like increase some of the element abundances here. Versus when you have fluxed melting, so this is melting with water present, you really start changing the geochemical signature. And really important here are the elements thorium and niobium. And you can use thorium or uranium. They're very similar, where niobium kind of stays really the same as the precursor mineral, versus thorium or uranium really start increasing. So now we can look at the uranium over niobium ratio in our zircons to understand, okay, is there any evidence for this hydrosmelting? Again, hydrosmelting is very characteristic of subduction zones where you put hydrated material into the mantle and you melt it. And when we look at the data here, so here's the uranium over niobium ratio. So if you have low values, then this is more characteristic of kind of juvenile settings and mantle environments, versus if you've got these elevated signatures here, it's very similar to modern arc environments. So when you look at the zircons, you can see that the majority of zircons prior to 3.8 have this mantle signature. So they don't have an arc signature or continental signature. And it's after 3.8 billion years ago that we start seeing more and more of these arc-like signatures. So, what does that mean? We are not entirely sure yet. This transition in the trace element really mirrors when we see the transition in the hafnium isotopes. So it could reflect an important transition in the geodynamic regime on Earth. But is it the onset of plate tectonics? I think is a much bigger question where we need more data. And then also, if you look here at the ancient zircons, you can still see some zircons that have this arc-like signature. So it could still be that there's maybe some form of subduction going on, maybe local, maybe episodic, maybe just less efficient. That's the first thing. The other thing is that, this type of arc-like signature, is something like very uniformitarian, right? Where you just assume, well, it's an arc-like signature like today, so that's the only process that can generate the signature, which is of course not true, because there's other kind of environments that might generate the signature that have been proposed for the Hadean. So for example, like drip tectonics, or you might have heard of sagduction, where instead of horizontal tectonics, right, where you shove one plate underneath the other, your crust kind of slowly starts dripping. And that might be another way to generate the signature. So just to summarize this, the oldest zircon that has been identified today, up to date, is 4.4 billion years old. So this might be some of the evidence of the oldest crust, but when we look at the hafnium isotopes, which really tell us when the crust was extracted from the mantle, it looks like some of that early crust formed prior to 4.4 billion years ago, so maybe as early as 4.5 billion years ago. But like having an exact age is really difficult because there's a lot of constraints that we need to know. So what types of crust were present? So based on the trace elements, we can see a lot of the crust was relatively juvenile. Some of it does have arc-like signatures. So there's some evidence for relatively diverse crust. Whether the zircons themselves formed an actual mafic or more felsic crust is still debated, although the majority of researchers, I would say, would suggest that the zircons formed in more felsic crust. So something like an andesite, granitic, TTG, something in that realm. And again, the question of what geodynamic regime did the early crusts form in, we're not quite sure yet. It's still a huge debate, and the field is really still kind of separated on that. All right, so let's start thinking about some of the other stuff we can learn about the early Earth. So again, one of the really important things for the evolution of early life is the presence of liquid water. So do we find any evidence for this, any evidence for liquid water during the Hadean eon? So this is something that people started doing in the early 2000s, and there's kind of two sister papers that came out together on the same day by different research groups, tackling the same issue with the same methods at the same time, and they come to the same conclusion. Based on the oxygen isotopes, they think that there's evidence for liquid water. So let me explain a little bit how they're doing that. So how does oxygen isotopes work? How can this help us understand presence or absence of liquid water? So oxygen isotopes are a really important tracer of kind of interactions between like a liquid and the crust. So when you have relatively dry crust with no evidence for like liquid water, so when we think about, for example, mantle zircons, they're going to have a really stable oxygen isotope signature of 5.3 per mole, plus minus 0.6. Now, if this crust gets altered with water either at high or low temperatures, it's going to shift the oxygen isotope signatures. So if we are like at the Earth's surface and we have low temperature waters interacting and altering like the crust or generating sediments, it's a process that has really high degrees of fractionation. So you're generating sediments or altered oceanic crust that's going to have elevated oxygen isotopes. So if this material now gets incorporated into your magma chamber, and then you melt that, and then the zircons form from that magma, the zircons are going to have elevated oxygen isotope values. So a little bit, you can see it over here. So this is for S-type granite. So S-type stands for it included sedimentary material. Now, on the other side, you can get really low oxygen isotopes. So this happens if you've got hydrothermal alteration of the crust, so at high temperatures. Waters at high temperatures, but especially you get really low oxygen isotopes if you have this alteration happening with meteoric water, so like rainwater on land if that gets incorporated. So we plot this up like this. So here are the oxygen isotopes. So here's the mantle field over here. So if we have zircons with this signature, it means that the melts were like dry, so it didn't kind of include this like altered material. But if you have values above that, this is your evidence for liquid water. So we can plot the data from the Jack Hills, and you can see it's a big scatter plot, but what's really encouraging is that we start seeing these really high oxygen isotope values really early on. So meaning that in the Jack Hills, since at least 4.3 billion years ago, so over here, we start seeing elevated oxygen isotopes, really confirming that there was some amount of liquid water present. So again, that's only one location. So I can add the data from the green sandstone bed in South Africa that I'm working on in white here. And so the zircons are not quite as old. The oldest that we found to date is 4.2 billion years old. And we see since like the oldest zircons here, like quite elevated values also providing evidence for liquid water. So, there was liquid water since at least 4.3 billion years ago. And now we've got two locations where we have evidence for liquid water. So that means that the liquid water was not just an isolated feature, but it may have been relatively widespread, but it's really hard to use that information to deduce that we had like vast oceans, right? Or maybe more like small little puddles. So that we don't fully know yet. But I would say that based on this data here, where we see evidence for liquid water in at least two locations. And then once we do actually have the onset of the sedimentary rock record about 3.8 billion years ago, like the sediments, like early on, they directly show evidence for liquid water. So it seems that like really early in Earth history, we started forming some amount of water and oceans. Again, how big they were is another question. So, this is liquid water, but then the next question is really, do we have any evidence for emergent crust? Many geologists, that worked in the early Earth kind of picture the early Earth as a sort of water world, which creates some challenges. So one, again, for numerous prebiotic pathways, the idea is that maybe that happened on land, right? Especially in the last couple of years, there's been a big shift towards origin of life on land, but for that you need some land, right? And if you generate a lot of continental crust that's sticking out above sea level, great, you're all set, right? You have got all of that. So it's, again, emergent crust important for prebiotic chemistry, but it's also really important for just like the atmosphere and the climate on Earth. So once you're merging land above sea level, it starts interacting with the atmosphere, and you kickstart silicate weathering, which is a thermostat, and it's going to keep the temperature on Earth more and more constant. So do we have evidence for emergent land? And there's a little bit of evidence, and it's very disputed, but I'm still going to walk you through it. And just to make sure we're all on the same page in terms of silicate weathering, right? So again, silicate weathering is this absolutely important process that's keeping our climate relatively stable. And what you do is that, when you have CO2 in the atmosphere, you've got CO2 in water, they form carbonic acid, which is going to rain out, and it's going to start interacting with the crust at the surface, so it's going to start weathering. And in the process, what you do is, you kind of like take the CO2 out of the atmosphere, and you let it react with the surface, and then this material is all being flushed into the oceans. So you've got alkalinity and cations that are being flushed into the oceans that eventually gets deposited as carbonates, at least during the modern Earth. So it's being taken out of the system. So if you have a lot of CO2 in the atmosphere, right, it gets hotter, which means that silicate weathering speeds up, so it takes out CO2 faster out of the atmosphere, essentially cooling Earth down. Now, if you're in a colder climate, it slows down silicate weathering, so you don't take as much CO2 out, so you kind of leave the Earth a little bit warmer. So again, it's sort of a thermostat for the early Earth. So what type of evidence are people trying to use to study the emergence of land? So there's two types of proxies that so far have been applied, and one proxy is for the presence and accumulation of meteoric water. So again, it's like, when you have kind of clouds forming from water from the ocean traveling and that raining out, that water is your meteoric water. And it's what's important with emergent crust is that you need a way to accumulate that water, right? So if you have evidence for a lot of meteoric water, this might be good evidence that there was some form of emergence. The other proxy that people use is evidence for the generation of sediments. So it's only really when you start exposing crust above sea level that you form your sandstones and clays and all of that. So we are looking for basically evidence that, we have emergence, you form these sediments, they're being deposited somewhere, and then they're reincorporated into your melt, and that changes the chemistry of the melt, which then we can track using the zircons. So do we have any evidence for the presence of sediments that were then incorporated into the magma? So again, the first one is the evidence for meteoric water, and to just make sure we're all on the same page. So for this, we are looking at oxygen isotopes again. And you can imagine when you have the ocean and it starts evaporating, the oxygen 16 is going to just evaporate a little bit more easily than oxygen 18. It's just lighter, and it's easier to like move that along. And then you form your clouds. The clouds are going to move along, and as the clouds are raining out, the oxygen 18, so the heavy oxygen isotope, is going to preferentially rain out, leaving the clouds progressively enriched in the oxygen 16. So when we look at the oxygen isotopes, right, as we go from the equator, we have more evaporation happening, and then kind of the clouds, you kind of start moving this way here, we start seeing lighter and lighter oxygen isotopes. Now, this meteoric water might accumulate in a setting like in a caldera where we've got shallow melting. So we've got the oxygen, like really depleted oxygen isotopes. We've got hydrothermal systems, which are also going to shift the oxygen isotopes like to more negative values. And so we are melting that material, and then zircons form from that, and we've got a really light oxygen isotope signature. So in general, the idea is that if you have your zircons with an oxygen isotope signature smaller than 3 per mole, then that's evidence for meteoric waters. And there was a paper just last year here published in Nature that suggests that they did find evidence for this type of meteoric water. So again, any values below about 3 per mole might be evidence for the accumulation of meteoric waters, like in a hydrothermal system. So there's some zircons here, 3 zircons at about 4 billion years, and then there's another handful of zircons here at about 3.4 billion years ago. So they're suggesting that this requires that at those time periods we had emergent land. Now, it might be evidence for it, but the number of observations here is really quite low. And ideally what we need to do is just look at more zircons, do more oxygen isotopes, throw some statistics at it to really make sure that these signatures are real. So this is a potential for emergence. It's not like your definitive proof. So the other thing that people have done to tackle this is to look again for evidence for the incorporation of sediments into your magma chamber. Again, like only when you really start emerging crust above sea level, you're generating sediments, and that gets like incorporated in your magma chamber, and it changes the chemistry of the magma, and that kind of change might be recorded within the zircons. And people have used different proxies, and there's really no consensus yet, because there's this early Nature paper here where they looked at phosphorus in zircon, and they're saying that the Hadean zircons crystallize predominantly from I-type magmas. So not showing a lot of evidence for like the generation of sediment. Similar here, this study by Ackerson, they look at aluminum as a proxy, and they're saying that, okay, for the Hadean, 90% of zircon show I-type signatures, suggesting that there was not a lot of emergent land. However, just in the last year, I think these are both from last year, these 2 papers, they're starting to use machine learning. So they're looking at the trace element geochemistry, they, of the Hadean zircons, comparing that to modern zircons from different settings, and then they kind of train the machine to identify any S-type zircons. And they get very different results. So here, in this study in PNAS, they think that 35% of zircons formed in an S-type setting, versus in this paper here, they say 45%. Sorry, the text got cut off, but 45% formed from S-type magmas. So you can see, again, the field is still divided. There's some possible evidence for S-type crust during the Hadean, but it's something that we really need to do a lot more research to really fully understand, to really know what is the best proxy that really tells us about emergence. Okay, and then I'm going to briefly talk about outgassing, which is, of course, really important for prebiotic chemistry. And here we are now going to start thinking about mantle redox. So you don't need to know all the details, but the redox chemistry of the mantle is basically determined by its oxygen fugacity, which is a measure of the non-ideal partial pressure of oxygen at a given pressure and temperature. So this is kind of like hard to conceptualize, but it's basically the idea, right? If you have iron, is it native iron, is it iron 2 plus, or is it iron 3 plus? So this becomes important because the FO2 has really bearing on the speciation of volatiles, right? Are you outgassing methane, or are you outgassing CO2? And that, of course, is very important for prebiotic chemistry. So the way we talk about outgassing here is we use buffer systems. So this is the QFM buffer here, and the details don't really matter as much. But basically, what you need to know that today QFM is at about 0, and if you're in arc environments where you have the disproportionation of water, you start raising the oxygen fugacity to a little bit higher values. So now zircons can track the oxidation state of the mantle, and that is because we're looking for redox-sensitive elements, and cerium is a really important one here. So zircon incorporates, here we're looking at the rare earth elements here in zircon. You can see zircons are generally enriched in the heavy rare earth elements. We also have some of the light rare earth elements, and cerium here is really the element of interest because cerium exists as 3 plus and 4 plus. So when you look at the partitioning of cerium into zircon, you can see, at low FO2, so when cerium is predominantly in the 3 plus state, it doesn't like to go into zircon. right? So, but once you start oxidizing your melt, you start forming more cerium 4 plus, and cerium 4 plus substitutes really nicely for zirconium into the zircon. So with increasing oxidation, we see the strong increase in cerium, and you can also see that here, right, from like more reducing, we have less cerium, and then we start really increasing the cerium abundance here. So there's a study by Dustin Trail in 2011, and they looked at Hadean zircons, and they're differentiating kind of zircons that form from the crust versus those that formed from the mantle based on the oxygen isotopes, as I was explaining earlier. And they found these 5 zircons over here, that show value of a delta FMQ of plus 1.4, plus minus 2. So it's only 5 zircons. And they have big error bars, but it's still like a really interesting study because although there's these big error bars, we do show quite positive values. And just to put this a little bit more into context, so when Earth first formed, it had actually a really low oxygen forgacity. So you would have really reducing gases outgassing. And then, especially through core formation, you start increasing the FMQ. And today, in again, our modern environments, we are close to FMQ 0 for the mantle, so plus minus 1 or 2. That goes as far back as we have a rock record. So the Jack Hills are suggesting, again, although there's a large error bar, that, during the Hadean, so pretty quickly, we had already oxidized the mantle. And long story short, why this matters is for outgassing. So if you look at that data, what you're expecting in terms of what's outgassing is, water, SO2, CO2, nitrogen. So that's very similar to today. So we don't expect to be like a whole lot of carbon monoxide or methane outgassing. No, this might be a problem for prebiotic chemistry if you're a big fan of the Urey-Miller experiment. Everyone knows about the Urey-Miller experiment where you're producing amino acids in this really reducing environment here. So it doesn't bode well for that, but when you talk about people now that study prebiotic chemistry, this really reducing environment like long term might actually not be good for early for the origin of life. And it's still, you would still form abundant amino acids if you have the right conditions during the early Earth. So if you had like abundant iron and the oceans were pH buffered, you can still form these amino acids. So, in a sense, it's like a good and a bad. So because, you don't have these reducing values, but you still can get to the right conditions. All right, and then last but not least, I'm not sure how much time I've left. I want to just briefly talk about the magnetic field. So, today we've got the geodynamo, right? We have got this liquid outer core where you've got this iron alloy that's moving around, generating our magnetic field. And this is really protecting us from solar wind, so in terms of the erosion of the upper atmosphere, and it shields life from cosmic radiation. So now zircons can include, so zircon itself is not really magnetic, but it can include inclusions that might capture some evidence of that early magnetic field. So if you have kind of magnetic minerals in there. So this has been studied for a few years now, and when you know about paleomagnetism, usually they can tell you about the paleo latitude, so where you are with respect to the equator. So when you look at these middle inclusions here, all you can learn about is the field strength. So was there a field or not? How did the field strength change? And there's this researcher, John Tarduno, who published a number of papers. So he was looking at inclusions in zircons. So this is an inclusion in one of the ancient zircons from the green sandstone bed. And he was looking at the evidence here for some kind of magnetic field through time. And he was suggesting that, well, he does get a signature, right? So he does get some evidence for field strength here. Early on, it was quite strong, and then it kind of like reduced in strength and then increased again to modern values. And he says the data supports the presence of a geomagnetic field and the associated shielding of the atmosphere from the solar wind by 4.2 billion years ago. So this is based on data from the Jack Hills, and then 2023, he added data from the green sandstone bed. So the Jack Hills here are in orange, and the South Africa zircons are in green. And what he is observing is that he gets very similar signatures through time. So he's saying for both locations, the paleo field values are nearly constant between about 3.9 and 3.4 billion years ago. And he's suggesting because the field strength sort of varies with where you are with respect to the equator, that means, okay, well, if it's not changing, that means the crust is not moving. Because if the crust was moving, you should see changes in field intensity. And he's using this as evidence for a stagnant lid, right? So here now we're kind of like switching back to early crust formation. So this was a really big paper that came out 2 years ago. But there have been a lot of questions about the validity of this approach. So then there are some other researchers, Paulina et al. And some other people that went out to kind of test, okay, do the zircons really retain a paleomagnetic signature? Because like doing paleomagnetism is really challenging to start with. Doing paleomagnetism in teeny tiny grains is even harder. So they looked at almost 4,000 zircon grains. Then they kind of selected the grains that are older than 3.5 because that's really the interval of interest. And then they selected the grains for analyses to see, okay, if we just try to replicate what they did, do we get a similar signature? And what they're finding is that, the ones that have some kind of paleomagnetic signature, the signature is mostly coming from the outsides of the zircon. So you can see here we are zooming into one of the grains, the tip. So the red areas here are rich in iron, so that's where your paleomagnetic signature might be coming from. It's only on the outside. So you see it here too. Here's the zircon grain. The red areas are kind of, red and blue areas are where you have kind of a signature or a signal, and that's just coming from the outside of the zircons. On this paper here from Tang et al. 2019, even if there's sometimes a signature from the inside of the zircons, so from, for example, magnetite inclusions, all of those inclusions are either along cracks or they precipitated in pore spaces, suggesting that they are secondary. So this kind of raises the question, okay, they are getting paleomagnetic signature, but is what we are looking at even primary? Right, so and if it's not primary, we can't really say anything about the geodynamic field. So kind of leaving the question open when the geodynamic, when we start having a magnetic field on Earth. So the last thing I want to briefly talk about is kind of, okay, we've talked about the habitability of the early Earth. Some things look good, right? There's evidence for liquid water. We had crust, maybe some emergent crust. It's certainly in the realm of possibilities. So now the question is there any evidence for life in the Hadean? We are really far away of really knowing when life first originated, but there are some interesting approaches, for example, using molecular clocks that suggest, the last universal common ancestor might have lived as far back as 4.2 billion years ago. So the question is, do we find any physical evidence for life in these zircons? And people have gone out to find evidence for it, so looking for graphite inclusions. So inclusions rich in carbon. So here they, in this study by Beth and Bell in 2015, they collected more than 10,000 zircons. They started studying, they found 656 zircons older than 3.8, and that's really the interesting time period because that's older than the oldest sedimentary rocks. And of those 656 zircons, 2 had graphite inclusions, potentially evidence for life. They're being a little more mindful here, and they are only, of the 2 zircons, only 1 had a graphite inclusion that was not along a crack, making them feel like, okay, this might actually be a primary graphite inclusion from the zircon formation, versus the graphite along the crack might be, might have later infiltrated. So it might not be a primary signature. So, they ended up with 1 zircon out of these, more than 10,000 that they originally set out to study that was old and had a graphite inclusion. Now, so the next thing they did is, of course we can't look for fossils, but we can look at the carbon isotopes. And that's probably a repetition for most of you, right? But in biological processes, when inorganic carbon is used to make organic carbon compounds, the 12 carbon is more weakly bonded, and so it reacts more readily, so it's more readily incorporated into organic material. So that means we kind of, when we look here through time and the carbon isotopes, and we look at organic matter through time, it just tends to have fairly negative carbon isotopes, again, because it's incorporating the lighter carbon isotope. So it's a good proxy for life. So now they looked at the zircon and they analyzed it, the carbon isotopic signature of the graphite, which comes out to be minus 24 plus minus 4 per mol. So that's this data here. And you can see when we look at organic carbon, it kind of like falls right in the sweet spot, which means that it's a signature that is consistent with organic kerogen. Now, is this conclusive evidence for life 4.1 billion years ago? Of course it's not, right? It's really interesting, right, that we find like graphite with this light signature, and it could be consistent with life, but there's a lot of other processes that could explain it. So it could be, for example, meteoritic carbon, right? Like meteorites, carbonaceous chondrites, they have a huge range of carbon isotopes from like positive to like really negative. So it might be meteoritic carbon, it might be abiogenic carbon, so there's a lot of different explanations. But it's still an interesting data point that we have that, which could be, but again, it could not be. So originally this was interpreted to be consistent with organic kerogen, but it's a sort of thing that's hard to imagine. It's not like you have your little, microbe living in the shallow water column and like dies, settles down, and then that sediment gets incorporated into magma, and then the little microbe ends up like in your zircon. That's, that's not what's going to happen. So 2 years ago, Vogt et al. Published a more refined interpretation of what this could mean. And they did this by studying graphite inclusions in younger rocks, where they kind of know the origin. They can kind of refine a little bit better of how that graphite, the carbon, might have gotten into the zircons. So here you see the younger zircon here with a dark spot. They did some Raman mapping, and here you see in red the graphite signature here within the zircon. And the interpretation they're coming up with that you don't just have like organic kerogen and that somehow gets into your magma and then your zircon forms. No, what is a more likely interpretation is that you have some kind of sedimentary rock that is rich in organic carbon, and then you have some kind of intrusion that's really hot. So you've got the contact oil, so you're sort of starting to kind of degas it, get out the carbon and the hydrogen. So you form these carbon, oxygen, hydrogen enriched fluids, and at the same time you've got your zircons like in this area here, which in the process they're kind of starting to dissolve again. So you don't see a nice crystal structure, but you kind of see this embayment here, which is a signature of, the zircon slowly dissolving. But in this setting, we've got the zircons and we've got these fluids migrating, and those fluids might be captured in some of these embayments. So these kind of like protective shields. And then you kind of form your new magma, and so you have an overgrowth of the zircon. So they're showing that, all the graphite they're finding is associated with this process where you're kind of like precipitating, material that was derived from organic, rich sedimentary rocks. So this is a more refined interpretation. It's still, in the interpretation, requires some amount of organic carbon. But again, was it really sedimentary? Was it really life? Was it maybe meteoritic in origin? Was it abiogenic carbon that had a light signature? That's really unknown. But it is clear that you kind of need a light carbon isotopic precursor in order to form the zircons. But really, yeah, is it truly early life? I think that question is still very much open. All right, so just to kind of finish up, looking at the different aspects that I've been, promising I would tell you about. So what have we learned about the lithosphere? So early crust evolution, we learned that, crusts did start forming pretty early on, and that it was like fairly long-lived, right? It remained stable for several hundreds of millions of years. It was probably quite a diverse crust, but the exact geodynamic setting is something that's really still up in the air. There is evidence for liquid water, and that in at least 2 locations now, so not just like one little puddle, but maybe 2 little puddles, who knows. But maybe vast oceans, right? Kind of that's the big question. And there's some possible evidence for local emergence, but it's really something we need to address more. In terms of the atmosphere, it seems based on this early study from Trail et al. That there's some evidence for outgassing that was actually quite similar to today. And it would still permit prebiotic chemistry just under the right conditions and potentially with the help of meteorite impacts. And then in terms of evidence for geodynamo and early life, those aspects are really still very much debated. So this is kind of the picture of the Hadean Earth that I think a lot of people have in their minds now after several decades of Hadean zircon research. And with that, that's it. So thank you so much for your attention, and I'm looking forward to your questions.